In this video we're going to look at Born-Haber cycles. Now if you haven't already, I strongly suggest that you have a look at the video on Hess cycles, and there'll be a link up here for that. Very briefly, to recap Hess's law was that if you start with chemical A and you finish with chemical B, it doesn't actually matter which route you take. If you take a direct route from A to B, or if you have an intermediate C, and you make that first and then make that into B, or if you even go through multiple intermediates like this, it doesn't matter. The total sum of the energy in or out from A to B is always the same regardless of which route you take. The Born-Haber cycle is an energy cycle that's constructed to work out if we had an ionic lattice, how much energy would we get if we took a bunch of positive ions and a bunch of negative ions and they all came together just to make the solid straight from isolated gaseous ions. This is a question that Born and Haber, it's the same Haber as the Haber process, they came up with the idea of doing it by an energy cycle, basically using Hess's law. So if we take our elements in a standard state and we react them together, we can actually make an ionic lattice that way. So we can measure delta H enthalpy change of formation directly if we wanted to, in this case. And that would give us our ionic lattice. The equation for that would be something along the lines of this. So our sodium is solid, our gas, our chlorine is gas. Note that we only need half a mole of chlorine, Cl2 gas, to every one of sodium. And that would make sodium chloride. So if we can't measure directly the energy change between the ionic lattice and our gaseous ions, then we need another way to get to gaseous ions from the elements in the standard state, and that should have the same quantity of energy going that way as we get in this large arrow here, which is our lattice energy, which we're trying to work out. Now, obviously, our lattice energy is represented by this equation, gaseous ions being Na plus gas, Cl minus gas, goes to NaCl. So we've got a downwards arrow here to show that that is going to be an exothermic process. So the first thing that we can do to our elements in standard state to turn them into gaseous ions is we need to get them into the gaseous state. So to do that, we're going to atomize them. And so with the sodium, the solid sodium, we would need to turn into gas, so we're going to need to melt it, then we're going to need to evaporate it, and we can call that the energy of atomization, starting in its standard state. And then the chlorine, we can do the same. We can take half a mole of chlorine gas. We need to put enough energy in to break the bonds between the chlorine atoms, so we're breaking apart the chlorine molecule, and that's going to give us Cl gas, just as single atoms. So obviously that's going to take quite a lot of energy. We're going to need to put energy in, so the arrow is going up. This is an endothermic process. And that gives us the atoms of just atoms on their own. Next thing that we're going to do is, and I'm going to do this in 2 steps, we've got to make the atoms into ions, and obviously if we're going to get one which is positive and one which is negative, there's going to be 2 processes in here. So if we want to make a positive ion, we've got to remove an electron. Again, that's going to be endothermic. we're going to put in another arrow upwards, and that's going to be this equation here, which you should recognise as the first ionisation energy of sodium. And the second one is going to be this. We have the chlorine atom is going to gain an electron. Now, because that's the opposite of ionisation, we're adding an electron on. It's going to be attracted to the chlorine. The nucleus of the chlorine is positively charged. It's going to accept that electron, and that's actually going to release energy. So this one I'm going to show as a downwards arrow here, and that's electron affinity. And then we have the gaseous ions, and we have a cycle. So our enthalpy change of formation makes a mole of our ionic lattice from elements in the standard state. To get the elements into the standard state to the atoms of the elements, we need to atomize them. In order to change the atoms of elements into gaseous ions, we need to use the ionization energy to make positive ions, and then the electron affinity is going to be needed as well to make the negative ions. And that should give us a value of lattice energy as this difference here. So to put that into an equation, we can see that if we start here, at the elements in the standard state, we have two routes. We have the delta FH, is one route, down to ionic lattice, and the other route is atomization, ionization, electron affinity, lattice enthalpy, and all in the same direction of the arrow, which means that the enthalpy change of formation is equal to the sum of the atomizations added onto the ionization energy, added onto the electron affinity, added onto the lattice enthalpy. And then we can take this equation and we can substitute values that we know for this, 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 and this, rearrange it, and we'll end up with lattice enthalpy.